terbium oxide, Tb2O3. Terbium is a trivalent, but calcium is divalent. So there is imbalance. But if there is a matching of ionic radius, right? So we can dope it. It depends upon what is the application, right? So here, I mean, our aim is not to use any chemicals, right? Our aim is to concentrate more on the recycling waste. It may be agriculture waste, maybe food waste, or it may be industrial waste. So with the help of these sources, we are trying to, synthesize so many material. I have shown a list of material in the last class. CaSiO3, calcium silicate, to number of nanomaterial. I mean, all R comes under the category of calcium silicate nanomaterial. Calcium silicate, CaSiO3, and then Ca2MgSi2O7, CaMgSi2O6. Not only this, there are plenty of metal are there, which we can able to prepare by means of using this particular material, right? So whereas if you take chemicals, if you adopt some chemical routes, right? So for example, if I want to make calcium silicate, So what are the precursors I want to use? First I need to decide. Getting my point or not? So what is the source of calcium oxide, right? So we need to take calcium carbonate or something else. For example, I want to make use of some material and I want to make the silica or SiO2. What is the source? So TeOS is a source, right? So many sources of silica are there, but the purity is very high for those material. So we are going to take a source. From that source, we will try to extract calcium oxide. We will take some other source of silica. We will extract silica from that, and then by means of selecting the composition 1:1 ratio or 1:2 or 1:3, we are going to get either calcium monosilicate or calcium disilicate or calcium trisilicate, right? Or you will get some other material. If it is a chemical route and if you are using chemicals, right, and if you want to make it, so you need to use number of material. For example, I want to make the acarbonate Ca2MgSi2O7. If I want to make it by means of using chemicals, so I require a source for calcium oxide, I require a source for magnesium oxide, I require a source for silica, right? There is one more material where you will try to get calcium, magnesium, silicon, iron and oxygen. So if you want to make it, I need to use more number of sources. Getting my point or not? If the structure is changing and if you see here, so I want to tell you the significance of these recycling waste. So if you see the calcium silicate based nanomaterial here, so for the first one is wollastonite, calcium silicate, and the last one is bactite. So what is the composition there? So we having calcium, zirconium, silica and then oxygen, right? Calcium zinc is there in the hardistonite. The mervinite you having calcium magnesium silicate, brigadite you having calcium magnesium silicate. See, the compositions are different. Suppose if you want to fabricate these nanomaterial or synthesize these nanomaterial with chemicals, for the last one you require calcium source, calcium oxide source, zirconium source, silica source. Similarly, mervinite if you want, you require source for calcium, magnesium, silica, oxygen, right? But as far as the recycling waste is concerned, right, So you try to use the combination. No need to dope anything here. No need to dope any magnesium. No need to dope whatever structure you want. In some cases, you will get even iron also. Why? Because in those recycling waste, the trace element, we may have zirconium, we will have iron, we have the titanium, right? So many metal are there. So the selection of the material, selection of the composition, right, will be decided by the type of recycling waste you are trying to use. So we can uh, synthesize any one of these material. All 10, even more than 10 are there. I think 20 to 25 are there by means of using recycling waste. No need to use additional dopant to this particular material, right? So we will try to get the desired material as I show you in the previous class. As shown in the previous class, right? For example, so I mentioned here. So waste contains a trace amount of metal oxide such as titanium, titanium oxide, magnesium oxide, iron oxide. So without doping, right, you just select properly the combination of recycling waste. So what we have done in our research for last 8 to 9 years. So our major research, we have used ricer as a source of silica with the eggshell as a source of calcium oxide. By taking 1:1 ratio, right, we have we have synthesized calcium silicate. 1:2 dicalcium silicate, 1:3 dicalcium silicate, right? So that is the thing we did, and similarly we have used GGBS and then flash. As both are the sources, I will try to show the composition also. Both are the sources for calcium oxide as well as silica oxide. Along with that, we will try to have titanium, magnesium, iron, and so on and so forth. Right. So by means of using the proper, material, proper combination, right, we have prepared acarbonate material, and this acarbonate is having very very important properties. Not only acarbonate, calcium silicate material. I have shown 10 material, 10 different composition to you. All those 10 or 12 or 15 compositions we are concentrating more because they are multifunctional material. They are having diverse applications. So we can use the same material for tissue engineering application. We can able to grow the heart tissues. We can use as a filling material. We can use the same material for phosphor application, luminescence application, right? We can use the material as a phosphor application by means of doping with required color, whatever color you want. We can use the same material for fabricating the optoelectronic device. We can use the same material for energy storage applications. We can use the same material for the photocatalysis also. That's why it comes in the category of multifunctional materials. So if you see here, this is the simple methodology. I think you explained this in the last class. Yeah. So they explain about how you are going to prepare this particular material, right? So first we are going to extract calcium oxide from eggshell, silica from ricers, right? Similarly, you can extract silica, calcium oxide either from GGBS or fly ash, right? So this is the procedure they have followed. This is sol gel. Similarly, have you shown hydrothermal? So they will try to show hydrothermal today if possible. So this is regarding the biological point of view. So I won't go much about the fundamentals now. I will directly jump into the application part. So this is the work done by Pooja for last 4 years. So her work is related to the development of normal supercapacitor material for the storage applications, and she has used the recycling waste, especially she has used the GGBS and then fly ash for her work. So she has done, I mean, a lot of work. So I don't want to explain. I'll try to show some results. So you know about the capacitor, right? So this is the different types of capacitor you used to come across, right? We have EDLC, pseudo capacitor, hybrid capacitor. So now when you are talking about energy storage devices or supercapacitors, right? Selection of metal is very important, right? So here we are trying to, I mean, develop the electrode material. Then when you are talking about the electrode material, anode or cathode, right? So we need to, the first one is the cost. The cost is very important, right? Otherwise, see, it should be affordable way, because when you, I mean, I think you know about the capacitors, right? Diode, right? How much the cost of a capacitor? Capacitor, resistor, right? So you cannot fabricate a capacitor whose cost is about 1 lakh or 2 lakh. If you go to market, right, few rupees if you spend, you will get it. Even resistor, capacitor, or diode, whatever it may be. So people are more towards the cost. Not only the, I'm talking about the, I'm not talking about the final product. I'm talking about the initial stage, right, where you are trying to get the material and then you are trying to give the final product. In between, there are so many steps which are involved to give the final product, right? So we need to check each and every source is important, right? From where you are trying to get the source and what all material is involved. Then man hours is also important, right? Your time is also important, effort is also important. Then after fabrication, before going to release into the market, so there are so many tests which you will try to come across, and once it pass the test, right, it will release in the market. Even after the completion of this course, right, we will try to conduct a test, right? We will give some grade and then we will give the certificate. Even you are doing BTech, MTech, right? So entire semester you will do the course, but how you are going to check your performance? You will try to conduct minors, mids, end exams, right? Then you will try to do some calculation, finally you will try to give the grade, right? So that is the test what you are going to do. Similarly, there is a test for the material which is going to convert into the device, right? Once you test the, I mean, pass the test, it will try to release in the market. If you won't test, then you will try to get R grade or F grade. You need to repeat the course. Similarly, here also we are going to do so many combination of the material, right? So don't think that within a day Pooja has done some cell and has she has used some sort of, I mean, cell she has fabricated and she has blown some LED or something else. So to prepare a coin cell or to make a supercapacitor, she has make an effort of 3 years or 4 years, right? First to do all these things, long-term stability, high specific surface, right? Then high electrical conductivity. And similarly, there are, I mean, role of electrolytes. We used to use NaOH, KOH, right? So many electrolytes are there. So why you need to select? Because of this particular, I mean, these are properties, right? The electrolyte, whatever you are going to select, it should have high ionic, I mean, conductivity, low viscosity, chemical stability is also important, easily available, right? Once again, the cost effect. So this is very important. Where you get it, right? So because we got, I mean, a source, right? The recycling waste. So the initial investment is very less. So one of my friend from civil engineering department, right? He is working in the industrial waste related material, like the iron ore industry, right? Where you will try to get this GGVS and then the fly ash. So he has given some amount of fly ash and some amount of GGBS, and when you are done the XRF, we found that there are so many elements which are trying to present in that particular material. As I mentioned, calcium silicate, calcium oxide, silica oxide, titanium oxide, zirconium oxide, iron oxide. Those are the constants. So then we found that this is a source for us to make our structure, right? So that's why the investment cost is very less. So what is that? It's a waste. It's a waste material what you have collected from the industry, and that is the fourth. The source for our research, right? So if you want to improve the performance of the supercapacitor, we need to consider these things, right? So the electrode, so the metal is important. Which metal you are going to? So the supercapacitor is not a new one, right? The energy storage is not a new one. It's already there, right? We are trying to improve its efficiency, right, by means of selecting the material. Not only and the material, so we need to concentrate on the surface area also. If you want to improve the energy density of the material or the power density of the material, which is very, very important. You are using the batteries in your cell phones, right? So what is your requirement? What is your requirement? It should charge fastly, right? Within no time, within half an hour, 15 minutes, it should charge, right? Because you are going to use 24 into 7, 365 days. This cell phone always with Facebook, WhatsApp, and so many things, right? But when we, during our, not during our research, when I joined in a job, right? So one of my friends used to have cell phone. At that time, it was Motorola, right? So he used to keep charging for the entire day. Those days, for incoming also, they used to charge. For not only for outgoing. Suppose outgoing is 10 rupees, incoming is 5 rupees. Right, later it was reduced, and the charging is very, very, the lifetime of the charger is very, very less. So if you want to use for 5-6 hours, we need to put the charge for 10 to 12 hours. But now how many hours you are going to put for charging? Not hours, less than that. Right, that is because of the batteries. Right, so zirconium, right, so many zirconium based batteries are there. So if you want to enhance that, right, so the power density is very, very important, right? The energy density is also important, right? And then the charging, discharging time also very, very important. If you want to, concentrate more on those properties for the device, so we must concentrate on the material. Then the surface area, the shape, size. So this also plays a significant role as far as the electrode is concerned. And then the interface between electrode and electrolyte, that is also very, very important, which is a part of your supercapacitor. And then what type of electrolyte you are going to use. So in our study we are using the liquid type, right? We are using KOH, NaOH, and some other electrolytes, right? So we can use solid, we can use liquid, we can use molten, and here also the concentration is also very, very important, right? With 2 mole percent, 3 mole percent, 7% mole percent. So the concentration is also important. Then the conductivity, viscosity, this will try to influence the performance of the electrolyte. And then the separator, right, anode, cathode, then the separator, right. So that is also, it is just like a membrane which will try to helps to transport the ions between the electrodes, anode and cathode. So all these things will play a significant role as far as the supercapacitor, or with help of supercapacitor you are going to make a cell, right. So this is the criteria for choosing the material. So lot of literature is there. So I told you it's not a new one. So lot of and those are the electrode they are used. We have two electrode type or 3 electrode type, and that is the specific capacitance. Similarly, you can calculate the power density. Okay. So as I mentioned earlier, this is the fly ash. This is industrial waste. It's a byproduct of from coal industry. You are going to get it. This fly ash. These are the constituents of the fly ash. This is the XRF data, X-ray fluorescence spectroscopy data. So here we are having 63.1 of silica, See here, aluminum oxide is there, 23.3, iron 6.5, right? So calcium is 2. Calcium is very less here, right? So we are going to take this as a source for silica. So the beauty of this particular, see, you can ask flash is a source for silica. Similarly, I have shown some other sources like rice husk I have shown, peanut shell I have shown. That is, those are also sources of silica. But we are going to use this because the yield is more here. The yield is more here. The output what you are going to get it from this will be more. So here the wastage is less compared to your rice husk because the yield may be 14% for the rice husk, whereas 3 times I'm talking about flash. That's why most of the cases you are going to use flash. This we got it after doing so many experiments. Even I don't know about the yield of flash. So every time we used to have the rice husk for silica, right? So for 100 grams we used to get 14 grams of silica. 100 grams of rice husk you took, we got 14 grams of it, right? But when you took this as a source, we are getting 3 times. The yield is very, very high for this particular thing, right? So that's why you use this one. And similarly, this is one of the industrial waste once again, the GGPS, right? This we are going to get it from iron ore industry, right? Wherever you have the ore industries, we are going to get the byproduct is GGPS. And when you record the X-ray fluorescence of this, see here the previous one silica is 63, now it is 30. But in the previous case calcium is nearly 2.93, here it is 48.8. That's why we took the previous one as a source for silica, this as a source for calcium oxide. And so many methods are there: hydrothermal, then co-precipitation method, solar thermal, sol gel. So many methods are there, but among them we are going to use the wet chemical method, which is simple, and where we will try to get more amount of the output. So these are the characterization techniques you use. We have XRD here, UV visible here, but XRF is not here. We are trying to get the characterization result from IIT Roorkee. Then we have PL here, we have BET in the in the institute, FECM in the department, right? FTR is also there in the department. So I use the characterization facilities whatever available in the department and in the institute, and other characterization techniques here from the other institutes, right? So this is the dip coating technique what I used to prepare the supercapacitor, right? So we require a binder. So PVDF I use a binder, and solvent I use NMP, right? So we use nickel form. Not only nickel, we use other material also. I'll try to explain later stages, right, in the coming slides. Similarly, this is 3 electrode model, where we will have the counter electrode platinum, then the reference electrode or silver chloride or silver, and working electrode is our material. The working electrode is our material what you have prepared, which is nothing but the acarbonate. And this is the setup we are in the department. With the help of that, we are trying to do the electrochemical studies. And similarly, we have done laser irradiation also. This is also there with mechanical department. And then we have the optical microscope to see the pore studies. See pore area, the surface areas are very, very important. So the surface area, the pore studies, we are going to get it by means of BET. And then if you want to change the surface area, or if you want to change the pore area or pore size, we are going to irradiate. So by using the laser irradiation technique, we are drastically improve the performance of the electrode. So we are use neodymium YAG laser, which is there in the mechanical department, and this optical microscope we are use. I'll try to show the images also, and then we are done the contact angle measurement also, which is also very important to see the addition of the material with the yeah, this is the method to fabricate the coin cell, right? So we have coin cap, the top and the bottom, then the spring which will try to hold your coin cell. There will be a spacer, and then your coat electrode. So material what you have prepared, we are going to coat, right, which is in the middle, right? So there is one more, and in between there is a separator spring, right? And you are going to apply some pressure, make it a compact cell device. So initially, as I told you, we followed the sol gel technique, and then with following sol gel technique by using GGBS and flash as a source, right? We have prepared calcium, silicate based nanomaterial, and the structure is Ca2MgSiO7 is the chemical formula, and which is known as the acarbonate, right? So here we optimize the temperature. So we are done from 600 degrees, we proceed up to 1100 degrees. So we found the structure, right, of acarbonate around about 950 degrees Celsius. So initially what we did, we optimized the composition, we optimized the temperature, which is very important, right? Even we have done some refinement, and then we observe from the refinement that there are two phases which are present inside the metal. One is the acarbonate, that is the major phase. Other one is the diopside. Even if you see the diopside, so what are the constituents of diopside? We have calcium, magnesium, iron and silicon. We didn't dope anything. We didn't dope anything. We use the same sources, GGBS and then flash, right? So major phase is tetragonal shape structure, and minor is monoclinic. So those are the lattice parameters, and then space groups. So this is the field emission image of the material, and then that is the EDS. So from the EDS we can confirm that those are the elements which are present inside the material, and the and similarly we have confirmed by means of FTR also. We have done some PL studies also. So this PL is because of the iron which is present inside the material, and the transition among those levels will give the output in terms of red color. So it is about 690 nanometers. So that color what you are getting is because of the trace element which is present inside that particular acarbonate structure. So similarly we have done different combinations, right? So if you see here, we are given some sample code, fly ash GGBS ratio 1:1. Fly ash is 1, GGBS 1. Then fly ash is 1, GGBS is 0.2, 0.8. Then 1:2, 0.6, like that we have varied. So we have done 10 different compositions. So our aim is to optimize the composition. Among this, which is the best one, which is suitable for our application. So I am explaining within an hour, but it requires a lot of time, right, to do the experiments. If you won't get the results, you will try to get irritated, right? And then if you won't get the slot to get the results, you will get irritated, right? So many things are there. So we will try to learn patience, and then how to face, how to write. So many things we will try to learn during our PhD, right? Sometimes guide also will try to scold you. You are not showing the results. So that also we need to face, right? So we have done so many combinations, right? So now we are having so many techniques, right? So if you want something, you will try to search in net. right? But during our PhD, right, we don't have any literature, right? So if I want to collect the literature, now you will try to put some keyword, electrodes or energy storage, supercapacitor, we get lot of data. But during our days, we had to travel from our institute to IIC Bangalore, IIT Delhi, right? We need to spend 10-15 days where in the library from morning 10 to night 12. I'm taking the special permission. We will try to, there are racks, right? I mean, have you ever went to library of your institute? You won't spend in library, right? You'll spend in your room with laptop. That is sufficient, right? Even I'll get the data in my cell phone. But those days, we need to go to library, to several racks. In that library also, if you go to physics, in physics, we'll have nuclear science, solid state physics, so many areas, electricity, magnetism. So I need to find my research area. Then I need to select the papers. Then I need to go to Xerox shop. I want to get Xerox of my material. So we have to go several times. So I have spent almost 1.5 years for literature. Then I need to study the papers, note down the points, then decide the composition. Then that is first thing. Then theoretically is I done, but practically I have to perform. I want to prepare some glass. With that combination, whether I am going to get the glass or not, there is a question mark. I done some soil studies. Whether I am going to get that structure, I don't know. Because now I prepare some material, I will book a slot in my laptop or in my cell phone for XRD. So in the evening I will go to the XRD, I will characterize, right? I will get the result. If I won't get, then I will prepare the sample. But in our days, we used to make 10, 20 or 50 samples, right? Then I had to book the slot, not in our institute. Once again, to IIC Bangalore or IIT. There, I mean, we need to go personally, right? So if I won't get any XRD, if I won't get any result, once again, I have to prepare the material. Getting my point or not? So many. Now, if you go to, the labs, what professor has shown in the morning, even there is a university in Dubai, right? So they have all sort of instruments, even synchrotron is they are having. So if you prepare the sample in the morning, right, in the evening, by evening or by night, you will get all sorts of results. XRD, FTR, FECM, TM, if it is having, PL, or whatever ellipsometry has shown, everything you will get it. If you won't get your desired results, then you can change the composition, you can do it. But to get a paper, to get 2 papers, our lifetime was over, right? So now your literature survey will be reduced. No need to go to Hyderabad, IIT or IIC, Bangalore or IIT Delhi. You can spend your time because you have free access to internet. You can download your Elsewhere, Wiley, Taylor series, right? So many papers. You can, only thing is that you need to read it. And nowadays you are having simulation also, right? You will try to give calcium, silicate, magnesium. What are the compositions you are going to get it? We see we are not doing simulation here. She has done so many combinations of the material to optimize the composition, right? And she has she has done different sintering temperature from 600 to 1200, right? So even simulation also can do it. We can get the result. We can able to optimize the temperature. We can optimize the. So first of all, we require to know. Now we are doing the reverse engineering, right? What is your requirement? Where you want to work? Whether you want to work in energy storage, or you want to work in solar cells, or you want to work in photovoltaics. So you need to understand the properties which you require for your applications, and who are all the material try to give these properties, right? Then you are going to select the material, right? So as you are doing some dish at your home, you are going to select. You are making biryani, right? What are the concepts required? So in a similar way, we are going to do it, right? Okay. So this is, to find out the crystalline temperature. So what is the TC of your material? So we are going to characterize with TGDTA. With TGDTA, we got the temperature for this particular material, and uh, with the help of that temperature, we optimize. So these are the different combinations, and those are the constants of the element they are going to present after preparing the material. So what is the temperature? So crystallization, it will try to exhibit at 1000 degrees Celsius. That is the temperature we optimize, and we found that the 1:1 is the better option. Fly ash and GG base 1:1 is the better option, and it is having the structure at the optimization temperature of 1000 degrees Celsius. And so this is the BET studies. From that, you are going to get the surface area, pore radius, which is very much essential for this type of studies. And similarly, we have found the energy band gap of the material also, which I explained to you in the beginning of the class. This is the XRD. So from this, right, XRD, we can observe that the major phase is acarbonate, and then the minor, the diopside, and one more structure is anorthorite, but major is the acarbonate. We are confirming from XRD. And similarly, to make the device, before going to make the device, we need to study the CV, GCD, and then GS studies characteristics. So that you are going to do by means of the electrochemical workstation, and the cyclovoltammetric studies you are going to do it. So from this, we are going to get this is the mechanism which is going to happen here, and this is GIS studies. From this, you are going to get the specific capacitance of the material, which you are going to deposit on the electrode. So we are going to use the symmetric electrodes. We are using the material both for anode as well as the cathode. So this is the device she made. See here. So the top one, the upper one, is the nickel form. Then FG 1:1, it is our material what you have prepared, right? And separator we have used, that is the face mask. The face mask we have used, right? And then the lower one also the same thing. And she made a device, right? And it will be of that form. And then she charged first, and she by means of giving 4 volts, right? And then discharged to LED, to watch, and then that calculator. So it helps to glow LED. It helps to glow. That clock or the calculator. So one by one it won't come. Pooja, एक के बाद एक नहीं आएगा. उसको एक के बाद एक नहीं होगा. So the first one, so she has charged that particular supercapacitor by applying 4 volts. The first one, yeah. Switch off the lights. So it's glowing. LEDs are glowing. Second one. Similarly, she has a charge with the 4 volts, the supercapacitor what you have prepared, and it is used to it is discharging through that watch, electronic watch. Charging you are doing by giving the external power supply, and is discharging to that particular. Similarly, this calculator also. So it is having discharging time of 51 seconds, 24 seconds, and 30 seconds. It will try to take 54 seconds, almost all 1 minute. So we want to improve that to few minutes. Similarly, by means of changing the electrode, so we optimize the composition as 1:1. That's the base composition, where flash is 1 and GG base is 1. That ratio we took, and then we are done. In this case, we optimize the electrolyte. So we optimize the electrolyte. Because that is very very important. So you should have the high conductivity, ionic conductivity, where the transportation of the carriers should takes place from electrodes, from this electrode to that electrode. So we have chosen the electrodes like KOH, NaOH, and different combination, and we confirm that 3 mole KOH a best one by means of our results. So there are so many reasons are there. So once again, you have done the electrochemical workstation studies, and we are trying to calculate the energy density and then power density, which is very much essential as far as the supercapacitor applications are concerned. And then finally we fabricated a device, right? So here these are the parts of the device. So those the red one, they are the electrodes. So we have used our material. So we have used our powder on a nickel form, right? And then we make a compact cell by means of using a spacer and then a spring. And then we have done number of studies, 1000 cycles, 4000 cycles we have done, right? And we have done the coin cells, right? So and then we are trying to power up these electronic gadgets like the LED, the watch, and the calculator. So here you have developed 2 coin cells. So we have used 5 volts to charge the cell, right? You can see at the top. So there are 2 cells, right? They kept in between an LED, the top. So those are the 2 cells which are developed here. We are charging to the power supply. So we given 5 volts, right? So here it is about 1, and then you are connecting a LED there, one red LED. So it discharging to LED, so it is trying to glow. You can see here, it's glowing. So the voltage across those cells is about 1.7. Similarly, you are trying to glow this watch. So we are giving a voltage of 5 volts. So it is discharging through the clock. So that watch. Similarly, you are trying to glow this calculator also through the cell what you have developed. In the cases, you see the graph, the voltage is about 1.9, 1.3, 1.4. So it is trying to take 35 seconds, 20 seconds, and then almost 1.5 minute to discharge. So we want to improve that particular timing so that we can able to use for more time. So the kind cell was what you have developed by means of optimizing the composition, optimizing the electrolyte. Similarly, we are trying to improve the surface area. We are trying to, enhance the power density and then the energy density. So, as such, the few studies related to the laser irradiation, not for this type of studies, for some other studies. So we thought of why can't you try for this particular method where you can able to enhance our the energy density and power density. So we took the help of our a colleague in the Department of Mechanical Engineering, and then we are done irradiation studies by means of varying the frequency, varying the wavelength, and other factors, right? So that's what I discuss here. So here these are the parameters, right? We are consider when you are doing the studies. So one is the wavelength, the frequency, the output voltage, the spot radius where you are going to irradiate the sample. That is also very important. So we are tested with not only with the nickel form, we are tested with stainless steel, we are tested with copper, we are tested with graphite. So what I want to say here, the material what you have prepared, we are going to deposit on different types of samples like copper, stainless steel, nickel form, and graphite. So among these studies, we found that nickel form is having the best results with scanning speed of 750, and then the spacing between one space to other space is about 150 micrometer. So different combination we did. So this is the contact angle we measured, which is also plays a significant role as far as the adhesiveness is concerned between nickel form and your material. So this is the optical microscope image of stainless steel, copper, and so on and so forth. So we have recorded the FECM image of the material which is deposited on the nickel form. So from EDS analysis, we can see the presence of our material also. We can see the morphology of bare graphite, bare copper, stainless steel, and nickel form. And this is the optical microscope image. So this is the BET studies. So we are trying to determine the surface area and then core radius, which are significantly increased after irradiating with the laser. And we have done the electrochemical studies, CV, GS, and GCD. So where we observe that there is a significant increase in the specific capacitance compared to the previous studies, and similarly we are tested, right? So it was better compared to the previous results, right? So that's all. This is regarding the energy storage application or supercapacitor applications of what the material we have grown. So regarding the photocatalysis, right, I will try to explain during the demo. Both of them they will try to explain the device, how they have fabricated the device, and how they make use of those electronic gadgets. And I'm talking about the applications of those cells. They will try to give a demo right in the lab. Okay. So if you have any doubt, you can ask me. It's a break now. So if you have any doubt, you can ask me.
So it does silicon oxide aluminum Suppose if I want to synthesize only calcium oxide, how can I eliminate this flexibility on that?
For calcium oxide, we need to go for this.
No, sir, I just am asking. Because a number of compounds.
No, that's what I'm saying. Amount of material is also important.
Okay.
So we can eliminate some of the trace elements during the soil presentation. There are different methods. That way, we can't eliminate. First of all, you try to see what is the percentage. If you see GG base dash, the major constituents are silica, then calcium oxide, and then aluminum. And there are very less. They are very minute. You can eliminate them easily. By means of using proper what you call the salts, by means of using pH, acid and bases. So you can able to eliminate them, and then even you can able to keep in a microreactor or heat they go. And if still they are present, you can filter them. They are going to have. For example, you take calcium carbonate, right? So if you heat it, what happens? Dissociate the calcium oxide and carbon dioxide. Carbon dioxide try to get calcium. So it depends upon the solvent body of the solution, then pH, concentration. Right? So we have so many acids, so many bases, sulfuric acid, nitric acid, hydrofluoric acid, so many bases. Then you have to count. Then pH, concentration. Then you heat it, concentrate. But sometimes, some of them it is not. So you need to go for some of them. Okay, so no questions are there. Already our student, they have circulated the list of names, affiliation. You be carefully check it out, because today I am going to send it.